So restricting domains. So when the inverses of a function is not a function, the domain of the function can be restricted to allow the inverse of the function, the inverse to be a function. In such cases, it is convenient to consider part of the function by restricting the domain of f of x. So suppose we try to find the formula for the inverse of f of x equals x squared. Well, if we tried doing that, what we'd see is this would be turned into y. So y equals x squared. Well, we'd have to exchange my x and my y. So we get that x is equal to y squared. So if I tried to simplify it, solve it for just y, that means I have to do the square root of both sides. You remember that gives me a positive and a negative root. So we actually kind of have like two functions here. Y is either negative square root of x, or y is the positive square root of x. So like I said, this is not an equation of a function because the input of 4 could yield a 2 or a negative 2. So what we can do is we can kind of restrict how we look at x squared to make this work for us. So we see here we have x squared. And I want to have the inverse of this function. Which we can't graph because it's not a function. So what we see here is, like we said, we know we can't graph this. That's inverse ends up looking like this, and it's not a function. So what we can do is that instead of using my entire function, I can just restrict the domain and just look at values that are 0 or greater. If I do that, that means that if I want my inverse now, my inverse could just be the square root of x. Because like I said, we're just looking at positive values, meaning that we only have to look at the positive roots. So that's one way that we can deal with this. As like I said, we just restrict the domain because we know that in this case, I can actually get an inverse function that is an actual function. If I had all of this here, then what we would see is this. Then I would have to have this part here with the positive roots and the part here with the negative roots. So this is just what restricting domain does, is it just makes it so it's something that will actually have an inverse to it. Okay, so like I said, if we restrict the domain of x squared to non-negative numbers, that is, I just use x values that are greater than or equal to 0, then the inverse function, the square root of the inverse function would just be the square root of x. So for our very last problem is we have two more functions that both of these are a square. So they do not have an inverse. So you may want to graph these first, but take a look at them and figure out how can I restrict my domain so that I keep half of my function, so then I can do an inverse of it. So our goal is to really just kind of keep as much of the function we can while keeping it 1-to-1, so it does have an inverse function. Like I said, a moment and see if we can do that, and then come back, we'll do this together. So for A, just as a reminder, we had x squared minus 5. So we see it looks very much like x squared. It's just shifted down 5 units. So we want to keep half of this function. So if we look at this and we just sort of want to just keep, say, this half of it, this is once again the half where my x values are 0 or greater. So x has to be greater than or equal to 0. So this would be my domain restriction. Oops, there's an S in restriction. Because if I do that, now I have something that's 1-to-1. Let me make a little spot to finish this out now. So we don't need this part of the screen. So now what we have is we can look at x squared minus 5. Got my f of x. And then once again, if I want to just find the inverse, like I said, as long as I restrict this domain, I can have an inverse. So what we'll see is my inverse. Well, once again, would you say y is equal to x squared minus 5? We just solve for x squared, then we're going to have y minus 5. Oops, sorry, plus 5. Got a little ahead of myself. One step before that, switch my x and y's. X equals y squared minus 5. Then I would add my 5 to both sides. And then because we want y by itself, I have to do square roots of both sides. And as a reminder, when you do a square root, there's always a positive root and a negative root. So we're saying that y is going to be plus or minus the square root of x plus 5. Okay, because of this domain restriction, that also becomes, because when you do your inverse function, that domain now becomes a range. So our range now, we have to make sure that the range is going to be values such that y is greater than or equal to 0. Meaning that I don't need a positive and negative root. I just have to consider my positive roots. So f inverse is just going to be the square root of x plus 5. I write that down here just a little bit. There we go. And we'll graph it so you can see that it is in fact what it should be. So we see reflecting over that line x equals y, or y equals x. There, in fact, this is going to be the inverse. So we just kept that part of the function, and now this is the inverse. All right, so like I said, just as a reminder, what happens is when you do that domain restriction, it causes your inverse to have this restriction on its range, saying that my range now can only be positive y values because the domain switches becoming the range. All right, now for B, we had G is going to be 3x plus 2 squared. So that shift that we're looking at was an internal shift. So what we see is that this is everything shifted over. If we look for the exact center, right there, so that is where it's touching the x-axis. He went back and did this just to show you what that was. Like I said, so we have a x-intercept, meaning we have a 0. This occurs when x is negative 2/3. So that is why we have a negative 0.666 there at that breaking point. So that is my vertex. So I only want to keep half of my function. It's usually easier to keep this more positive half of my function. So I'm going to restrict the domain, so it has to be values that are greater than or equal to negative 2/3. Okay. So as I said, my domain restriction is going to be is restricted to this place where x has to be values greater than or equal to -2/3, because that keeps half of my function, half of my graph, and it keeps everything 1-to-1. So we're going to look for those inverses again. So we have g of x is going to be 3x plus 2 squared, or y equals 3x plus 2 squared. And this next part here is we're just going to switch x and y. So x is equal to 3y plus 2 squared. And now we need to solve for y. So first thing you need to do is get rid of the square. So I have to do a square root of both sides. So I get a plus or minus root. Plus or minus square root of x. So what we're going to see here in a minute is that I'm just going to end up keeping the positive root again because I kept my more positive side of my graph. I'm going to move my equals here. So what I'm going to be left with over here is just 3y plus 2. Then I can subtract the 2. And then I can divide by the y. So y is just going to be plus or minus the square root of x minus 2 divided by 3. Okay. So once again, I'm trying to keep more positive values. So what we're going to end up doing is we're just going to leave this like this. So we're not going to keep that plus and minus. We're just going to leave it as y is equal to the square root of x minus 2 over 3. All right, so sorry about that. I had to go fix the scaling so we could see this. So as you see, if I graph the other part of this, so my inverse function, we can see here. So we're at roughly, I'm a little off just a little bit, but this is, try hit 0. Yeah, it's not one to hit it exactly, but as you're seeing that we're having roughly about your -2/3, 0, and then this point is 0, -2/3. So we're getting that reflection again. Like I said, this one's a little hard to see because it keeps wanting to do the scaling a little off.